All right, to understand the types of covalent bonds, let's start with something simple. And what could possibly be simpler than hydrogen? This is H2. Hydrogen normally bonds, if it's in its pure form, it bonds monotomically. So H bonded to H, just like that, okay? In order to understand this, let's look at each one of these individually. So I've got HA and HB. So HA, so here's our A, this is H. What is the electron configuration for this guy? Well, it's going to be 1s. 1. It has one electron. One and only one electron. How about this guy? B, H, and it's also got 1s1. Both of these have 1s1. If I write out their their orbital diagrams, well, then it's going to look something like this. Right? I've just got a single electron in each one of these, 1s. So this is how they would look separated. If I put a line between these two, this is how they would look separated. But they're not separated. These two are bonded. Both of these are not stable on their own. And by not stable on their own, what I mean is their charges don't even out. Everything in nature wants to reach this state of pure evenness. In biology, we call this homeostasis. In chemistry, when we're talking about how things even out, we're talking about the evening out of electric charges. This is why we care so much about those charges, because it informs us of reactivity. So when these two bond, they're trying to balance out this absence of, and here, let's just use pencil, it'll look light, it'll be ghostly, this absence of an extra electron. They want those shells filled, and so in order to fill them, they will overlap their orbitals. Now there's a lot of complexity to this theory, so we're going to keep this nice and simple. We're just going to look at how these overlap. So here I've got my 1s from blue, and the same thing is overlapped by the 1s from red. And so my blue electron overlaps there, my red electron overlaps here. Okay? Now don't worry about this arrow flipping sides. It's arbitrary. It's just how we draw it. Don't worry about it. But when these two electron clouds overlap, now I'm going to have my two hydrogens. One here, just as little points. And their electron orbitals are overlapping. Now, if we remember bond strength and energy, well, the more energy, the more strength in this bond, it's going to pull together. Okay? It's going to be harder to pull them apart. If there's less, they might be separated a little farther. But regardless, the electron cloud here is attracted to both this hydrogen and this hydrogen. The electron cloud here is attracted to both hydrogens as well. And so it kind of spreads out to try and be in between both of them at the same time. There's still going to be some time that the electron spends over here, just a little bit, but most of the time it's going to be in between these. Okay? So when we have this type of bond, we have our s orbitals overlapping. The official name for this is a sigma bond. Sigma is a Greek letter. It's the Greek version of our S. That's why it's called sigma. It starts with that same letter S. So this is the s orbitals overlapping. It makes a sigma bond. Now, the letter sigma doesn't really look like a S at all. It's actually more like a squiggly O. That's what sigma looks like. Don't worry about that. Just this is a sigma bond. We have a sigma bond here. S orbital, sigma. S, sigma, okay? And then that's just the symbol that we use to describe it, all right? So let's look at something a little more complex, but still kind of on the same plane. Let's look at fluorine. Fluorine will also, ignore the scars in my table, fluorine also bonds just like this, F2. And we're going to give this that same treatment. If we remember our Lewis structures, fluorine has 7 valence electrons. 2 of them are contained in that bond there. So if I were to write out, using the same color combos, I've got my fluorine A, this guy's A. I could just call this fluorine blue, whatever. Its electron configuration is 1s2, 2s2, 2p5. Okay? And this guy over here is our fluorine B. Let's see if I left myself enough room. I'm going to have, let's just to make sure that I don't overlap here because I'm terrible at drawing. Got my B fluorine. See, I should have just done red and blue. F is 1s2, 2s2, 2p5. If I write out the orbital diagrams here, I've got it's going to look like this. So this is my 1s, 2s, 2p. Same thing over here. 1s, 2s, 2p. Okay? When I fill in my electrons, 1s orbital is full, 2s orbital is full, and there are 5 electrons in my 2p orbital, leaving me 1 empty slot. Okay. This is where things are going to get a little more complex. Because the thing is, these aren't just going to have overlapping p orbitals. Because if we remember our atomic orbital theory, if I just draw out just kind of a sketch of what one of these fluorines might look like, I'm going to use, I only have the 3 colors here, so I'm going to use black for S, I'm going to use blue for P. Okay? Blue and black aren't different enough. Scratch that. Red for P. There we go. That'll be a little more visible. So my S orbital on the F. This would be 1s. Here's my 2s. The 1s is completely covered by the 2s orbital. Okay? It actually kind of pushes that 1s orbital down into it. Then my p orbitals, I've got all 3 have electrons in them. So they kind of come out kind of like this. You'll have to imagine one coming out of the page at you and one going into the page away from you. My orbitals organize themselves like this. We never see fluorine like this. We never see it all by itself in nature. Because atoms don't just exist in a vacuum. It's not all by itself. If I've got a fluorine atom, chances are I've got 2 or 3 or 3 billion, more likely. Billions of fluorines all hanging out together. And so if I've got a fluorine here, and I've got another fluorine here with all of those same orbitals, the 1s, the 2s, and then my 2 p's, and again, there's one coming out of the page and one going into the page. Well, the electrons here, they're attracted to the protons, and here let's use blue for that, the protons in this nucleus. And so they're going to pull towards each other. And when these 2 atoms pull towards each other, the electrons in their clouds are repulsed by each other. These electrons don't want to be near each other. And so as these fluorines come together, forming this molecule of fluorine, this monatomic molecule of fluorine, the way they're going to do that, the way they're going to take on these new shapes, or I'm sorry, the way they're going to become stable is by taking on these new shapes. These orbitals are actually going to merge together and become what we call a hybridized orbital. This is all in an effort for these electrons to move away from each other to balance out their charge. All right? So that's the whole point of what we're looking at here, is that these electrons will move around each other in order to balance out a charge.